Okay, let's turn this thing on. I posted the answers to 10 of the problems on the sample test, because the first 10, because it looks like those are that's the material that we can really prepare for the test. The remaining problems we'll probably get to the basics of how one can solve those problems today, a lot of them at least, but that won't give us time to prepare those for the test. And so so the last 5 problems like the last 5 problems won't be on the test. So concentrate on the first 10 problems on that test review. That's a good 10 problems to use as a study guide, though, okay, for the test. Okay, so particularly the last few counting problems would be sort of the level of difficulty of the counting problems. Now, I'm going to give you back your homework number 2 today. So those solutions are posted. Homework number 3, those are a mixture of questions that you can probably do now, and then but they're mixed up with questions that you may not be prepared to answer until after today. So, but you should continue working on the homework 3 questions. Think about those questions. Think about, if you have approaches to solving those. But we probably won't make that due until after the test. But I still think you should work on those to help you prepare for the counting problems on the test. Okay, even if some of those are going to be a little bit too difficult for this test. All right. So again, the level of difficulty of those counting problems through the first 10 problems on the sample test would be a good guide for what to expect on test number 1. Okay, and so again, the solutions are posted there, right there with the right there with the sample test. All right. Okay. So I'm going to. Like I mentioned there, I'm going to give you back your homework number 2, and thought I would mention here some of the just a couple of the problems there that I looked at. I can't remember exactly the numbers of the problems that I looked at. One of them was the the last question from the book. That was problem number 42. That was that Christmas tree chessboard. I think they call it a stair-step chessboard, but you can also call it a Christmas tree chessboard. Because, let me see if I can make this work. Is this thing even on? No, that's why. Okay. So that was problem number 42. I didn't get. All right, so a lot of people made stab at that problem. Some of your answers were a little bit incoherent, so I couldn't. I don't know. Oh, this one? I don't know what that one. Okay, it's saying green now. I wonder if that means. I don't know where to plug that in, though. If I wanted to plug it in, but it's got HDMI, so seems like that should be. Wait a minute, let's try. try it again. Now it's off again. Okay. Okay, that's the name of the device. So that's there we go. All right. So we will. This is Chad's paper who gave an argument for this. So this is this this stair step or this Christmas tree chessboard, right, where some of the squares above a diagonal, right, on the top right there above the diagonal have been cut off of the chessboard, right, and the question was, is there a perfect cover for that? So the reason I call that sometimes a Christmas tree is if you turn it maybe like this, then the diagonal kind of looks like a Christmas tree, right? That look like a Christmas tree to you, sort of. Okay. So anyway, so I did get a lot of responses to this, and some of them I couldn't follow very well. Okay. So but you might have had the right idea. I just couldn't follow your reasoning very well. So I might have put a question about that. A lot of the responses were something to the effect that depending on the parity of the dimension, if this this is Chad. So Chad, I'm explaining your solution to this problem. Depending on the parity of the dimension, right, of the chessboard, whether it was even or odd, then when you marked off took out these squares, right, then that would leave you with maybe an even or odd number of squares remaining to cover, right? So if that's an odd number, then you could say, right, that obviously the remaining chessboard doesn't have a perfect cover, right? But I think if the dimension is even, then you're going to get still an even number of squares left. Is that right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, see, that's 10, right? So that's an even number. But if the dimension is odd, then I think maybe you do come up with an odd number of squares left to cover, which you cannot do, right? So here, the dimension is odd. This is 5 by 5, right? So 1, 2, 3, 4, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, right, okay? So I think that issue occurs, right? Whenever you have an odd dimension, after you've xed out the top right-hand diagonal, right, then indeed, right, you get an odd number of squares left over, so you're not going to be able to cover that. But if the dimension is even, then I do think you get an even number of squares, so you cannot make that argument. What? What now?
12 plus 9 is 21. That's an odd number of squares, an odd number of squares.
Oh, I see. So there, do we count that right, though? Oh, that's odd too. Okay. Oh, so it's a little bit more complex, correct? All right. As to when you get an odd or even number of squares left. Okay. All right. So, well, in any event, right? Sometimes you might be able to apply that reasoning, but apparently sometimes I think you cannot apply that reasoning. Okay. Chad's argument was that. If you look at the squares as colored, right, okay, which you would normally have on a chessboard, then Chad argued that he started coloring black here in the top left-hand corner, but that's okay. It could be white, right, okay? But he argued that, you don't have the same number ever of black and whites, all right, and therefore then you couldn't whether this is, whether the sum is odd or even or not, right? If you don't have the same number of black and whites, you're not going to get a perfect cover of the remaining part of the chessboard, okay? All right, so, but you didn't exactly, Chad, prove that the black and whites are not the same. You just gave me some examples there, all right? So that's a little bit of a flaw in the proof, but I still thought that was a good start of an argument, right? Okay? Better than just if we have an even number of squares left or an odd number of squares left, okay? All right. Now, some people, again, went beyond whether there was an even number of odd squares left and tried to make an argument to me about why it couldn't be covered, but I wasn't completely convinced by the arguments, all right, okay? They were either difficult to follow or I didn't find them convincing. You can read my argument in the posted answers, okay, which has nothing to do with how many squares are left, the number of squares left, okay, black or white or even or odd. My argument was, so see if y'all find this convincing. If you have to cover this square, right, okay, up here in the top left-hand corner, but you can't cover that with a horizontal domino, right? That's got to be covered with a vertical, right? That's the only way to cover that. So you know you're going to get a vertical domino here, okay? But once you put a vertical domino here, notice this square becomes isolated, right? Okay? And so the only way to cover this one is going to be with a vertical domino. You can't put a horizontal in there. So that must be covered with the vertical. And then you can just continue that reasoning, right? So this one must also be covered with the vertical. Correct? Okay? But eventually what happens is, if you continue that, again, that sort of, it's a stair-step pattern, right, of putting in these vertical dominoes, right? Then notice this one ultimately gets isolated, okay? You'll end up with this square isolated. It won't have an adjacent empty square to it, and so you will not be able to ever cover this one, okay? That one cannot be covered. So that was my argument for that. Does that make sense? Y'all follow that? Okay. Only way to cover this is vertical, right? But then the only way to cover this one was a vertical domino. But once you put a vertical domino there, the only way to cover this one is with a vertical one, and so on and so forth. And then this one ends up getting cut off. All right. So it will never get covered. Okay. In a perfect covering. That was my argument. Okay. The other one that was that I looked at was Cunan, and so many of y'all had a good good description of the winning strategy for Cunan. So that's the winning strategies, okay, in the two different versions of the game in Cunan. I don't know if Chad, if you put that one here or not. Yeah, you gave a description of that one also, okay, in yours. But many of y'all gave a good description of that. You can see that in the you can see that also in the posted solutions, okay? The more interesting game, though, is Poison Cookie, okay? So I posted really the wrong, not the version of the game that I intended to post, okay? Because when I was writing these questions down, I didn't understand myself Poison Cookie all that well. I only knew some things about it, a few things about it. So I posted the 6x6 version of Poison Cookie, which indeed has a winning strategy, okay? I don't know how many did y'all find the winning strategy for Poison Cookie. It's for player 2, however, right? Okay? The black player, right, yeah, okay. Black has a winning strategy. No?
It was white. It was white.
Oh, no, yeah, you're right. It's white that has the, right. Okay, player 1 has the winning strategy. I'm thinking backwards, all right. So, indeed, player 1 has a winning strategy, and if you look at the posted solutions, if you reduce that to a 6x4, so 6 column, or 4x6, one or the other, or maybe it doesn't matter, version of that game, okay? I think it's 4x6, where you have 4 rows and 6 columns. Then that's a much more interesting version of the game. So it turns out that you can indeed prove that white, player 1, has a winning strategy. So you can prove that, but no one knows how to describe that winning strategy, okay? So the only way to actually play that winning strategy for white would be to write a computer program that would explore all possible outcomes of the game based on whatever move the players makes, and then feeds to player one what the correct move would be in any given situation. Okay, but there's no known efficient way of describing the winning strategy for player one. Although player one does have a winning strategy, that's in the 4x6 version of the game. But in the 6x6 version of the game, Dalton or Kaylee, you want to tell me? And other people have said, oh, y'all know what strategy is as well, but they came to my office and were describing it to me, so I know they know. So y'all want to describe what that is?
Sure. It's a very simple way to do it. White goes first, so white picks this.
Don't have a 6x6 board, I don't think. Here. What?
So white picks.
Oh, here's one.
Yeah.
Okay.
Looking at the top right one, that's white's first move. It's like the first diagonal from the poison cookie.
Oh, so white would take this out first?
Yeah.
Yeah, okay, right.
And then simply copy what black does.
And then from that on, just simply mimic black's move.
Yep.
So white moves here and gets rid of most of the board, right? Okay.
Yep.
And then after that, whatever black does, white,
just mirror opposite.
the mirror of that, right? So if white moved here, right, for instance, then black would move there, right? Okay. Or if white.
It's more like if black moves there, then white would move there.
What now?
It's
it's black, right? So if black moves here, then white moves here, right? Okay, and then black moves there, white moves there. Okay, right. Okay, so you just played the same square, right? But in a mirror fashion, right? Okay. The only two columns you've got left are, you've got this row and this column left, right to play. So whatever black plays right, white would play that same position, but in either the opposite row or the opposite column, right? Okay, and in that case, then is it white? Yeah, white's guaranteed to win. Okay, so y'all can check that. All right, good. Okay, so I'm not going to go through my description of why on any size board we know that indeed white wins. Okay, but there is a description of that in the we know that white has a winning strategy for any size board, any dimension board, but again, in certain cases we don't know exactly how to describe that winning strategy. We just know that it exists. Okay. All right, so I had some people not turn in the homeworks right, and again, it's important that you make a stab, right, at all the problems, okay, because some of them I'm going to grade, some of them I'm not going to grade right. But even if you cannot, get the solution to the problem, you need to think about all the problems, right, okay, so that, of course, you may come up with a solution if you think about it, but if you don't think about it, then you won't. But all that thought, even if it ends up not getting you anywhere for a particular problem, eventually that's going to pay off, okay? Eva, right? On a test or in future homeworks. I know the problems sometimes are challenging, but so you just have to give it just think about it the best you can, right? Marion? And try to write something down, right, that indicated that you had thought about it. Eric, Julian, Sean. I think you're this. Are you this Sean? No, you're that Sean. Okay, I'm confused with my Sean's again. All right. So Dalton, Kaylee, Michael Palacios. Is Michael Palacios? Oh, sorry. Diana. Mr. King, is it Bradley? Bradley King? Catherine's here. John Garcia? John. All right. So if I wrote something by a problem and I didn't and I didn't put a check mark there or didn't count off, that means I wasn't quite convinced of your answer, but I thought you had at least put some effort into the problem, so I didn't take off. Okay. Again, some of these problems are hard and not always easy to arrive at the solutions. Right? They involve logic and creative thought, and sometimes you get it, and sometimes on that problem you just don't get it. Right? Okay. But again, that practice, thinking about the problem, that is eventually going to pay off. Okay. And it's I give this pep talk so often, right? It's purely a physical a phenomenon as to why that thought you put into these problems eventually is going to pay off, right? Because that thought is causing your brain to try to make connections between neurons, okay, that haven't previously been connected. It's like when you go to the gym, right, and you're lifting weights, right, okay? You're building your muscles. Physically, there's a change happening in your body. Physically, when you're thinking about these problems, there's a change happening in your body, right, okay? And just like at the gym, although it's a slow process, eventually you will get stronger, right, okay? Your muscles will grow because that's just the way your body is designed to work. When you're thinking about these problems, your brain doesn't really grow in the sense that it gets heavier, okay, right? But you're making you're forging new neural pathways in your brain, and eventually that pays off, okay, right? Those actual physical changes in your brain eventually going to make you smarter, all right? Okay, and that's why it's difficult too, right? Think about problems. It involves physical exertion. It's not the same physical exertion as in a gym, right, which is also unpleasant sometimes, right, okay, to be lifting weights or doing whatever exercise. But it's hard to do, right, because it requires effort. It's the same thing, that thinking requires physical exertion, so it can be tiresome, right? I mean, your body will say, oh, stop doing this, this requires work, right? But, we have to keep working at it. Okay. But I hope sometimes the problems are fun, right? So you can ignore those signals from your, body, right, to stop doing that. Okay, let's look at. Do y'all have questions? So I haven't. Again, I just mentioned, right, that maybe for some people came in, right, that maybe the first 10 problems from the sample test, the solutions are posted there. Those would be really the appropriate material for the test, right? So the problems after problem number 10. We're right on the verge of getting to those, but we won't be able to prepare those for the test because they involve the models that we're going to talk about today. Okay. However, a problem that is that would be good for the test is this one. This is another example from the notes. Okay. This is a problem that's actually in the book. So I don't know what page it's on, but you can. Find this in the chapter 2, this example. So it says, suppose you're going to, order the 26 letters in the alphabet. So you're going to build a word, right, out of the 26 letters in the alphabet. So that implies no repetition, though, right, because you're ordering the 26 letters that are in the alphabet, right, to build the word. But you want to do that in such a way that none of the vowels, A, E, I, or U, will occur consecutively, correct? Okay, so how many ways can you build a word, right? Or how many ways can you arrange the 26 letters in the alphabet so that the vowels do not occur consecutively? All right. So let's take this in an algorithmic approach. All right, and think about what we would do to build such an arrangement. Okay, and there are lots of ways of thinking about building the arrangement, but some of those ways of describing building the arrangement are going to be easier to count than others. Okay, so you want to come up with an algorithm or a description of the process for building a word that makes it easy for you to count. All right, and this one does require a little bit of cleverness. Okay, so the book's suggestion is first. Forget about the vowels for a moment that we don't want to appear consecutively, right? So forget about those. So think about in building up this arrangement, right, of the 26 letters, just go ahead and arrange the consonants first, right? Just go ahead and arrange the consonants first, right? So so we could write here, first step in our algorithm, right, or first choice, right, is to arrange the arrange the consonants. How many consonants are there here, right? Yeah, there are 21, right? So arrange the consonants first. Because after all, when you eventually get the entire 26 letters arranged, right, that's going to include the 21 consonants, and they're going to be arranged in some order, right? Okay, so you might as well go ahead and think of writing them down first, okay? So just arrange the 21 consonants first. And I think it's pretty easy to count how to arrange the 21 consonants. That's why I said, right, when you're describing your algorithm for building the arrangement, you know, you want to be able to count the choices you have at each step, correct, right? And I think it's pretty easy to see how many choices we have on the first step, right? That's going to be what? So if you've got 21 things to arrange, how many ways can you arrange them? 21 factorial, right, okay? That's just a permutation, right? When you write down this arrangement of the 21 consonants, that's just the permutation of those 21 consonants, right? So there's 21 factorial ways of executing this first step, okay, right, okay? All right, now, of course, obviously the next step here, our ultimate goal of the next step here is going to be you've got to get the vowels arranged as well, correct, right? Okay, so if you want to, you can go ahead and just think of this as arranging the 21 vowels, the 5 vowels, okay? But that turns out to be not so useful, okay, to write the second step down to sort of mimic the first step. So see, we can write the second step here as arrange the 5 vowels, right? Okay, but the problem with that is what? Well, we know how many ways we're going to do this, right? Okay, so how many ways can we arrange those 5 vowels, Sean? Well, no. Well, in the final arrangement of the letters, right? Okay, the 26 letters, you are going to have an arrangement of the vowels, right? Okay, the vowels are going to appear in some order, but not consecutively, right? But they're going to appear in some order, correct? Right? Okay. So if you're reading from left to right, you're going to hit a vowel, then you're going to hit another vowel, then you're going to hit another vowel, and that is an arrangement, correct? Right? Okay. So how many ways can we build that arrangement? 5 factorial. But see, the problem is once you have then said, okay, I'm choosing this way of arranging the vowels, right? You haven't built the word, right, yet, because what do you still have to do?
Put that into the consonant.
Yeah, you have to somehow insert them into the, somehow insert them in the word, right, okay? So they end up being not consecutive, right, okay? So although there are 21 factorial ways of arranging the consonants, that's fine, and 5 factorial ways of arranging the vowels, right? These two steps together do not build the final word for you, correct, right? You have to do now something else. And so that something else is what's hard to describe, right? That you said, what do you have to do now?
You have to somehow insert.
Yeah, you have to somehow insert them, right, okay, properly into the word, right, so that they end up not being consecutive, okay? And see, that's the part that's the little bit of the tricky part, right, okay? So starting off like this is, that's a way to think of it, correct, okay? But that's sort of not ultimately getting us to an arrangement of the 26 letters, right, one that we can count, all right? So I have a different suggestion now for the second step, okay? Let's just focus on there on A, okay? So we've got to get A there into the word, right? Okay? So, and A's got to go somewhere, correct, right? So let's just focus on putting in A, okay? So how shall I describe that step? Position the A, All right. Now, that's a much easier step, right? I think than. Well, I'm not sure if it's easier than how I described the second step before, but this is a pretty easy step, right? Okay. How many choices do we have for this step? Okay. So, yeah. So why 22, Dalton? Why do you say 22?
Because if you were to say 21, then that means you're either putting it only in front of a letter or only behind a letter. 22 involves, like, you can put it in front of the first letter and behind the last letter.
Ah, right, okay. So if you think of the spaces between the, you got to put A somewhere between these consonants, right, that you've already arranged, correct? So if you think about the spaces where you can put A, right, okay, well, I can put it between, somewhere between the 21 consonants, right, okay? How many places would that be between the 21 consonants? There are 20, right, okay? There are 20 places to insert it between the 21 consonants. But you've got to remember, you can also put it, what, as Dalton said, what, before
The first letter.
or after
The
last letter. So altogether, there are 22 places to put the A, correct, right, okay? If you think of those positions between the consonants, right, and then before the first consonant, after the first consonant. Well, once we've got the A down right, then what's our third step going to be here? Sure, right, okay. So let's position the E, right? And then, of course, so on and so forth here, right? You're going to have to position the, what are they? The I and the O and the, so that's the sixth step here. I'm not going to write down all the steps but explicitly, but you can see what they are, right? So the sixth step is position the U, right? So let's see if we can count the choices there, right, on each one of our sequence of steps, right, in our algorithm. So you already told me, right, for the first step, how many choices do I have there? What is it?
Oh, for the first step?
Yes. 21 factorial, right, okay? There's 21 factorial ways to arrange those consonants, because that's just a permutation of all 21 consonants, right, okay? So there's 21 factorial ways to do that. And then how many ways for the second step? We already discussed that. That's what? 22, right? Okay. 22 places we can put the A. Now, how many places can we put the E? Only 21, that's right, okay? Because A has occupied one of our positions, right? Okay. And now, how many for the, what is it? I? That's the third. That's the fourth step here. So what? 20, right? And then the O is 19, correct, right? And then, am I counting this right? And then finally the U is 18. Ah, there we go. Okay. So if we go through all those steps, will we have the arrangement of the letters? I think so, right? Because we placed all 26 of them, and none of the vowels are going to be consecutive, right? Because we inserted them around the consonants, right? Okay, so there's no way you can get right consecutive letters there. I mean consecutive vowels, right? See, so we can arrive at a number there algorithmically. Nice. So that's maybe the kind of level of difficulty, right? That you might not level of difficulty, but maybe that's the kind of problem, right, that you could handle on the test, right? Because it just involves models, right, for accounting that we've already talked about. I'm not going to do this example because that's going to take up too much of our time. This is a lengthy example, but you can find this in the book on page 37, right? Okay, that's a good problem. I would definitely take a look at that problem on page 37. That one involves lots of ways of sort of breaking down the problem. to make it to make the counting understandable. But I don't want to. But you can read that solution from the text. Oh, by the way, now make sure that you have gone back and reviewed the solutions that I posted. Right. So to the first homework, those solutions are posted. To the second homework, those solutions are posted. Right. And then also to the test review, those solutions are posted. So read those. Okay. And think about, see if you can understand the solutions to those problems, and maybe think about how that might have differed from your solution to a particular problem. Okay. All right. So I think finally someone here was asking, how do we arrange this question, right, about putting things in a circle. All right, so let's talk about how to solve this problem. It's really just a permutation problem. Okay, so how many ways are there to arrange the students in our class in a circle? Okay, all right. So let's cut this just to make this a little bit easier to illustrate. We've got 20 students in the class, but let's reduce this just a little bit so I can diagram it a little bit better for you. So let's reduce it to 6. So suppose we just got 6 students in the class, and we're going to arrange them in a circle. So we're going to number the students as usual, right? So we'll have students 1, 2, 3, 4, 5, and 6, right? Okay, and going to put them in a circle. So I think your first thought of this is, well, putting them in a circle is not. How is that any different from arranging them in a line, right? Okay, you're going to pick a person, right, to sort of start the circle, and then you're going to pick the person next to them, right? So you might say, okay, I'm going to go in a clockwise direction. So clockwise, who's next to the first person, right? And then got to pick the third person, right? And the fourth person, fifth person, and sixth person, right? That looks very much like creating a permutation, right? Okay, just an arrangement of the 6 students, right? Okay, so why is the answer here not 6 factorial? All right, because that would be our first guess here, right? If there are 6 students in the class. Let's write out a permutation, though, of 6 objects. So again, if we think of the students as being numbered, let's just use the integer segment 6, right? 1, 2, 3, 4, 5, 6 as a kind of a model for the class, right? And let's write out a permutation of that integer segment. So you want to write down a permutation for me of 1, 2, 3, 4, 5, and 6, but be a little bit creative. I don't want 1, 2, 3, 4, 5, 6 there. So just what's a permutation of? 1, 4. Okay. 1, 4, 3, 6, 2, 5. All right. So yeah, Dalton, I think you were mentally counting, right? Okay. Did you forget the first 6 integers? You sort of slowed down there at the end there, right? So, okay, all right. Yeah, so that's a perfectly nice permutation, right? So, okay, so you might think, right, that, okay, well, that permutation, then that clearly corresponds to a circle, right? Because I could put 1, and then if we're thinking of going clockwise, right, this is 4, and then 3, and then 6, and then 2, and then 5, right? Okay, so there's my nice play circle, right, for the students. Okay, but the problem with this is that well, that's definitely a circle. Okay, but the problem is that if you think of rotating the circle, right? Okay, if you think of rotating the circle, a certain amount, then that doesn't really change the circle, correct? Okay.
Dr. Wall,
Uh-huh.
is this similar to the problem where it's like the cube without the numbering and the cube with the numbering?
Yes, it's similar in a sense to that. Yes. Okay. Yeah, because here's what you have to consider in distinguishing between circles. Okay. Now the way I've written these on the paper you might say, oh, these two circles are different, okay, right? Okay, because they don't really look the same, right? Here, 1 is at 12 o'clock, and here 5 is at 12 o'clock, right? So in some sense, you might say that's not the same circle, right? Okay, and that does correspond. This circle does indeed correspond to a different permutation. Kind of what's the permutation that that second circle corresponds to?
5, 1, 4, 3.
Yeah, right. Okay, that would be 5, 1, 4, 3, 6, 2, right? Which is definitely not the same permutation as this one, right? These two permutations are not the same. But this is really the same circle, okay? Because what can you really, what really distinguishes one circle from another, right? Okay, as opposed to one permutation from another. In permutations, the position of the numbers is important, right? Okay, so these permutations are different because, well, they don't agree, right? For instance, in the same, in the first slot, right? Okay, so they have to be different permutations, right, Eduardo? Okay, yeah. But in a circle, how can you distinguish one circle from another? Okay. See, in a circle, the rotating the circle really doesn't alter the circle. Okay.
Well, the issue is that they're students, so you can't repeat students. So
Well, you can't repeat students in a permutation either, right?
Yeah.
Okay, yeah, okay. But how do you distinguish one circle different from another if the orientation of the circle is not critical here? Okay. See, permutations have beginnings and ends, right? Okay, but circles don't have beginnings and ends, right? Okay, circles by their nature don't have that. Okay, so but how can you distinguish one circle from another? Then, yeah, Kaylee.
Every element is going to have the same two neighbors.
It's by the neighbors of the elements, right? Okay, that's what's really important in a circle, right? Okay, you can distinguish one circle from another if, right, a person does not have the same people on their left and right. Okay, if they're thinking of facing in, right? If people do not have the same neighbors in the circle, that's when a circle is not the same. So these two circles are really the same circle, okay? Because everybody has the same neighbors, right? Okay. 4 is 1 and 3, right? 3 is 4 and 6. 6 is 2 and 3, right? Okay. These two circles are identical. So, Eduardo, what would be a circle not identical to this one?
just 1, 2, 3, 4, 5, 6.
Okay. 1, 2, 3, 4, 5, 6. All right. I'll buy that. 1, 2, 3, 4, 5, 6. All right. But how can you tell that this circle and this circle, this circle and this circle are not the same? So if I said, looks like a circle to me, right? Okay. Their circles are round. All these things are round. So how would you know that these circles are different?
Well, for each number, you look at the previous circles, like 1, 6, 2, and the previous one, 1, 5, 4. Then you go to the next number, 2, 1, 3, 2, 5, 6, and you go through, I guess.
No. Okay. I mean, maybe that's right, but how can you say that more succinctly?
They don't have the same neighbors.
Who doesn't have the same neighbors?
The new circle, and I guess the
Who? Who, though?
student.
Yeah, which student?
Student.
Student 1. Yeah, fine. Yeah, right. Okay. Yeah, that's right. Okay. So think of student 1 as, think of the circle as facing in, right? Okay. So on student 1's right is here in this circle is what? 6, right? Okay. And on their left is 2. But up here, who is student 1's neighbors? 5 and 4, right? Okay. So student 1 does not have the same neighbors in this circle, right? Okay. So those two circles are different. By the way, if you had sextuplets here and you're putting them in a circle, then how many different ways would there be of doing that? Sextuplets, means there's 6 identical people, right? Okay. So how many ways can you arrange sextuplets into a circle? Only one, that's right, okay. There's only one way of doing that, right? You put them in a circle, and that's it, right? Okay. You cannot distinguish one circle from the next, right? Okay. All of them look the same to you, right? Okay. So as far as you're concerned, right, everyone has the same neighbors, right? Okay. So there's only one way of doing that. See, the being able to identify objects or not being able to identify objects really makes a huge difference in counting, right? Okay. All right. But Eduardo, so this number is too big, right? Okay, because this counts the number of these straight line permutations, right? Okay, but we already saw that these two permutations are really the same. Correct? As circles, these two circular permutations are really the same, right? Okay? But as straight line permutations, they're different. So we've overcounted. This number is too big. So the question is, how much have we overcounted? We're going to have to adjust this, right? Okay? To get the right answer. So let's think about it. Which group of permutations is going to give you the same circle? Right? We know these two permutations really gave us the same circle. What other permutations will also give us this same circle?
From the first set, like 1, 4, 3, 6, 2, 5?
Yeah, from this one, right, we saw this one was really the same circle, right? So we can't count this twice when we're counting circles, right? But what's another permutation that's going to give us the same circle as these two? Notice, how do we get from here to here? Yeah, you just shift, right? Okay. So here we just shifted the 5 and pushed everything back. So what's another one, Shelby?
1, 4, 3, 6, 2, 5. Oh, no,
That's the first one, right? So.
Going backwards, right? 4, 3, 6, 2, 5, 1.
Well, what about this one? 2, 5, 1, 4, 3, 6. I'm going to move the 2, right? Is that? I'm just trying to be systematic here. And then we can move the 6, right? So I get 6, 5, 1, 4, 3. Oh, what's left there? 2. Oh, I did it wrong. Oh, yeah. Okay. So 6, 2, 5, 1, 4, 3. Is that right? And then we can do that again, right? So 3, 6, 2, 5, 1, 4. Can I do it again? So 4, 3, 6, 2, 5, 1. And then if I do it again, I'm back to this one, right? Okay. All of those, right? All of those permutations will result in exactly the same circle, correct? Right? Agree, Eduardo? Yeah. So how many of those are there? 6. So what do I need to do here to adjust the correct number? Yeah, see, each one of these 6 permutations, right, led to really the same circle. So I've overcounted the number of circles by a factor of what? 6, right. So how do I fix this number? If it's overcounted by a factor of 6, divide by 6, right, sure, right, okay. Just divide by 6 there. So the right answer there is here. I want to divide by 6. Notice that reduces to what? 5 factorial, right, okay. Now you can answer the actual question here, right, which is we have 20 students in the class, right? So how many ways can I arrange them into a circle? There you go. It's 19 factorial, exactly right, okay. Just subtract 1 and then put factorial on that, right, okay. Does that make sense now? What's really important is noticing how you can distinguish between two circles. How can you tell that two circles are different? And the only way you can tell is by the neighbors of the individual students, right? This idea comes up repeatedly in counting. How can I tell two objects are different? Okay, right? Okay, for counting purposes. All right. Sometimes that seems like that's an obvious thing, but it's not always so obvious, right? Okay. Let's see. Let's make a variation on this then. So suppose Sean and Sean there, right? We're going to sit them together, okay? So if you want to sit them together, how many ways can we do this? All right, so in effect, Dalton, you're going to think of the Sean and Sean as being what? Just a single...
Just a single, like, pair almost?
Yeah, like a single unit, right? Okay, so how many things are you really arranging in a circle?
5.
No, I've got 20 students, right? So how many things am I really...
So
19, right, okay, because the two Seans are always going together, right, okay, so you're really just arranging 19, right, the 18 other students and then the pair, Sean and Sean, right, okay, so that would appear to give me what? 18 factorial, right, except I think there's one little exception here, right, okay, what is the, I'm off by just a little bit, all right, because in the pair, right, the Sean and Sean pair, what can I do? You can flip their positions, right, okay. So how many ways can I flip their positions? 2, right, okay. So I have to take this number as almost correct except what? Times 2, right, okay. If you want to describe that as an algorithm, what would you say? Oh, I think exactly what we said, right? We would... put the what? The 19 objects, right, that we have to arrange, right, the 18 students and the pair, right, into a circle. Okay, so we would make that circle, right, okay, and then we would decide on what? The order of the two Seans, correct, right, okay, so put the pair, Sean and Sean, right, plus the 18 other students into a circle, and then decide after you've done that, there's 18 factorial ways to arrange them in a circle, then after you've done that, decide how you're going to arrange the two Seans next to each other, okay? All right, so the answer there is just 2 times 18 factorial. This problem is interesting, but so I'll leave this also for the book, okay? How many necklaces can be made from 20 different beads if each one is a different color? That sounds like arranging the 20 students in the class in a circle, right? Okay, so it sounds like 19 factorial, but the book has an interesting a little catch to this problem, so you can read that in on page 44, okay? The answer is essentially 19 factorial like you would think, except the book is going to claim that some necklaces that appear to be different, that we count differently, are really the same necklace, okay? So y'all can read that. All right. Now, so we want to move on now to a new model, okay, for modeling sets, a new type of set model. So what have we seen so far, right? So we've talked about set partitions, correct, right? And helping us count sets, which are really disjoint set unions and complements, right? Set cross products, right? We've used this a lot, okay? And then sets of permutations, which is really kind of a derivative of a set cross products, all right? But now I want to show you just a new set model that you're probably familiar with, most of you, okay? And it also is kind of related to permutations, all right? So suppose you have a set. It's got to have at least one element in it. I suppose you can, make these definitions with the empty set, but it's kind of a boring definition. So suppose you've got a non-empty set, and you pick some integer that is at least 1, but less than or equal to the size of the set. So any integer between 1 and the size of the set that you're starting from, right? So you've got some sort of base set, right, that you're working from, okay? And then, an R combination from S is just any subset out of S, okay, of cardinality R, all right? So if you have a set with a given cardinality n, right, and then you have and then you pick a number less than or equal to n, and you take a subset of that size from the given set, that's called an R combination. All right. So so R combinations are like R permutations, right? Except in R permutations. R permutations are arrangements. They are lists. So the order in which you list the elements makes a difference. But an R combination is a subset. And remember, in sets, the order of the elements is not important, right? Okay? So that's the difference. In an R permutation, that also involves a subset of a set. But the subset is arranged in a particular order. In an R combination, the elements in the subset are not arranged in order. Okay. So, for instance, suppose we take as our basis set here the integer segment 9, 1, 2, 3, up to 9, right? Okay. Then these are going to be permutations, right, of elements from that set. These are 3 permutations, correct? Right? Because you've taken 3 elements of the set and you've arranged them in a particular order. So these 3 permutations are all different, because although they involve the same 3 elements, right, 1, 5, and 7, because the arrangement in order is different from left to right, those are different 3 permutations. However, if you just take those 3 elements of the set, right, and think of them as a subset of the original set, then that would be called a 3 combination, and these 3 combinations are all the same, because they're subsets, okay, right? So these 3 permutations are different, but they all are related to the same 3 combination. These 3 subsets are all alike. So notice you're going to have more R permutations than you have R combinations, right? Okay, the number of R combinations is less than the number of R permutations. So what's the basic difference between an R permutation and an R combination? If I ask this on the test, R combination is a what? Subset. R permutation is an ordered list. That's right. Okay, that's a list where order makes a difference, but an R combination is just a subset. Okay, just a plain old subset. And sometimes we like to model sets by R combinations, not R permutations. So here's the counting theorem that's going to be useful to us, right? So suppose you have a set again, right? And let C be the set of all R combinations. So you have a particular choice of R there, right? Okay. So let C be the set of all R combinations from that given set. Then here's how you can count that set of all R combinations. So it's n factorial over R factorial. By the way, that is the way you count the number of R permutations. Right? Oh, no. I'm sorry. This is the way you count the number of R permutations from the set. Okay? And then to get the number of R combinations, you have to divide out by this factor as well. Okay? Because there are fewer R combinations than R permutations. Notice, what do these 2 numbers in the denominator add up to? N, right, okay. So notice they add up to N. So this value and this value add up to N, right? Now, the book, there's a couple of notations for this particular quantity, all right? And again, that's the number of R combinations. Here's one notation that you can use, C, and then with the N and R here in parentheses. But here's another way that represents that same quantity, all right? So in this big set of parentheses, put N over R, okay? This is the notation that you'll see most frequently. Although technically this represents a number, I am often going to use that notation for the set of all R combinations. So I'm going to frequently use this notation to represent a set, not a quantity. Okay? This always represents a quantity, however. All right? So this is just shorthand notation for this computation. This, by the way, goes by another name. This is called a binomial coefficient. We'll talk later about why that's called a binomial coefficient. You may be wondering, binomial, that's a term from algebra. How is algebra coming into play here? Okay, well, that's an interesting question. So we'll get back to that question later. But these computations, again, go by the name binomial coefficients. All right. So easy to apply this model now. So simple problems using R combinations are very easy to answer. So let's see. So how many teams of size 5, I think we've done this type of problem before, right, but with different restrictions. How many teams of size 5 can be chosen from a class, from our class, right, for a combinatorics competition? So how many different 5-member teams can we build out of the class? Well, if you select a 5-member team from the class, that obviously is just a subset of the class, right? Okay, of size 5. And how many subsets of size 5 can we build from the class? So let's let the set here we're trying to count. Let's call that S for the set of teams, right? So what is our model here for S? When you pick a team of size 5, you're just picking a what from the set? A subset, right? You're picking a what? Or did you say permutation? Yeah, no, okay, yeah, because the members of the team don't have any particular rank, Shelby, okay? They're just a team, right, okay? So they're all equal. So you're just picking a subset of size 5, okay, from the set, okay? So the set of all possible teams is just the set of 5 combinations from the class, right? How big is the class? 20, right, okay? So the set model we can use for this is set of combinations from a set of size what? 20, right? And how big do we want our combinations, our subsets to be? 5, right, okay? So remember, I often use this notation to represent the set of all combinations from a particular set. So this would be the set of subsets of size 5, right, from a set of size 20. Of course, what's kind of the generic set of size 20 that we usually refer to? Well, it could be the class, right, okay? But what's an even more abstract model for the class? Integer segment, right, yeah, the integer segment 20, okay? So when I write this down, I mean from the integer segment 20, 1, 2, 3, up to 20, how many subsets of size 5 can we pick from that, okay? That's what that notation would represent, right, okay? And of course, that's a model of course, picking 5 students from the class of size 20, right, okay? Which is the same as the set of teams. So what's the cardinality of this then? Right, that is that so-called binomial coefficient. So that would be 20 factorial, right? Okay, divided by, what's the size of your team? 5 factorial, right? And then, how many people are not on the team? 15 factorial. By the way, when you pick a subset of size 5, of course, then you're automatically excluding 15 students, correct? So you have another, implicitly, you're also picking another subset of size 15, right, okay? The excluded students. Of course, the 5 on the team and the 5 not on the team, those two things are complements of each other, right? Those two sets are complements of each other, right, okay? Because when you join them together, you get the whole class, right, okay? So another way of thinking of building combinations here is how many ways can you partition a set into a set and its complement, right? Okay, a subset and its complement, I should say. All right. Because that's what we're doing here, right? We have the team members and then the people not on the team. Now, of course, you can compute this, right? Okay, and many calculators will have keys, right, or functions that will allow you to compute this directly, all right, without having to do any intermediate computations. I'm not going to do the calculations there. Oh, by the way, you may wonder, and this is a good question, why this is the case, but of course, this number of teams of size 5 has to be an integer, right? I mean, you can't have a fractional number of teams, correct, right? So you know that the answer to this question is an integer. So this quantity has to turn out to be an integer. Okay? You may be wondering, why didn't that turn out to be a fraction? Right? Okay? I mean, you've got a lot of factors in the numerator and denominator, right? Why do you not get a fraction here? Why do you always get an integer? That's a good question, but that's always going to be an integer. Okay? So that will always reduce to an integer. Yeah.
Why would it be a fraction? Because, I mean, it's the set of teams, so it has to be
Yeah, so we know logically it has to be an integer, right? Okay? But if you weren't thinking of it logically, if you were just given that computation,
if you were just looking at the numbers.
yeah, you might say, how come this never turns out to be a fraction, right? Because there's lots of factors in the numerator and denominator. Why does everything reduce, right? Okay, why do I get lucky and I always get a fraction here? I mean, I always get an integer here, right? Okay. How many teams of size larger than 2 can be formed? Larger than 2. Yeah, okay. So again, think of complements, right? Okay, think of complements. All right. You may want to. Let's let S be set exactly what we're counting here, right? Set of teams. So one way to count S, this is kind of the laborious way here, right, would just be to say, okay, teams larger than 2, that would be what? What numbers are larger than 2? 3 to 20, right? Okay, so I can start by seeing how many teams of size 3 I have, right? Okay, so how do you count that? That's right, okay, that's this binomial coefficient, okay. Oh, I didn't say how to read that off of the page, okay. So that's 20, and you usually say choose 3. That's a nice way to read that, right? Because that's what you're doing, right? From the 20 students, you're choosing 3 of them, correct, okay. But 20 choose 3 means all possible ways of doing that, all right. So that's one way, but then you might have a team of size what? 4, right, okay, and all the way up to you might have a team of size what? Might send the whole class, right, okay, so it's pretty obvious what this is going to be, what? 1, right, okay, there's only one way to pick all 20 students from the class, correct, okay, but now these other numbers, so that's a lot of calculations, right, okay. Well, that'll do it if you're patient, all right. What's another way here? Do the complement, right. So what's S bar then? In words, how would we describe the complement?
Set of teams with 2 or less. Or less than 3. Say less than 3.
Yeah. Set of teams 2 or less, right? This one I think now is much easier to count though, correct, right? So how many teams can you have of size 2 or less here?
Do you have to include the set with 0 people in the team?
No.
Then
Yeah.
20 choose 1, 1 choose 1.
Right, yeah. I'm worried about this. Okay, we'll come back to whether we have to consider the team of size 0. All right. So S and S bar here are clearly complements of one another, right? So we should be able to count S, right, by subtracting S bar, right, from the size of the universal set here. What is, though, the universal set?
The set of all.
Set of all teams, right? Okay. So let's let T here be set of all teams. And how big is the set of all teams, though? It's 2 to the 20th, that's right. Chad, why is that 2 to the 20th power? Yeah, that's right. So we already answered this question, right? Okay. So in a previous notes, we already answered how many teams there are altogether. It is 2 to the 20th power, but this does include the empty team. Okay. So we have to be careful. I guess in S bar we would include the team if we're going to use this as our a way to count this. We would include the empty team here, okay? All right, so there's the answer, all right? Of course, you have to compute 2 to the 20th power, right? And then add these up and subtract, but that's, I think, still a lot easier, right, than trying to add up all these binomial coefficients, all right? That's a lot of calculations to do, okay? Yeah, we did this in a prior notes, okay? I'm glad, Chad, you remembered how we did that in the prior notes, okay? All right. We have just this time, maybe. So what if we're going to have, we want a diverse team, right? So we're going to have 3 math majors, 1 data science major, and 1 computer science major. How many teams can we form? So that's 5, okay? But we want to have just this combination of the majors represented in the class. So 3 of the math majors, 1 data science major, and 1 computer science major. So think about picking the team here. How could you actually form the team? What steps would you take there to build that team? Yeah. I think so, right. So what could you do first here if you're thinking about building up a team? Yeah, how many math majors are in the class, though? We know this, right? There's 12, right, okay? So what would you do with those 12 math majors? Yeah, first you would pick the 3 math majors, right, okay? So you would pick the 3 math majors first, and how many ways can you do that? 12 choose 3, right, that's what you just said, okay? Right, okay? So that's our first choice in building up the set, correct? Okay? Then what would you do next? Whatever choose 1. How many data science were there? 2, right? And then we would choose 1 of those, correct? Right? Okay? And then, last one, right? That's the computer science major. We're going to pick 1 of those. How many computer science majors did we have? 3, right? I think it was 3, right? Okay. So see, so here you're combining actually approaches, right? Because we're actually thinking of this as actually selecting the team, right? So we're describing an algorithm for actually selecting the team. First, I would pick the 3 math majors, but I know the way of picking the 3 math majors is 12 choose 3, because those 3 math majors are going to be a 3 combination, right, from the set of math majors, right? And then one way of picking out of the data science majors, you really don't have to think of this as being a combination, right? There's two data science majors to pick. You pick one of them, so there's two ways of doing this, okay? If you choose one, that will give you two. And then there's three computer science majors. We're going to pick one of those, right? Okay, there's three ways of doing that. If you calculate this value, you get 3, all right? So pick the math, pick the data science, and pick the computer science, right? Okay, and that will form the team, right? Okay, so there it is. That's the answer. Oh, yay, we're out of time here. Okay. So I had some. We got some more variations on this that are fun. Okay. So we'll get to those after the test. All right. So. All right, if you want to come by my office, come see me. I'm there a lot tomorrow in the morning, okay? And I'll be there later this afternoon after about 3, all right? So if you want to discuss answers to any of the questions, feel free to come talk to me, all right? And I'll see y'all on Wednesday.